So what is kinematics? Well, it's just giving the position of the end effector and the orientation. Differential implies the change in the position. So when this change in position, it basically means something like dp or dxc, dy, and so on. And so that derivative change is basically what one way of saying the change is basically the velocity if you divide by dt, and then something else called Jacobian. We'll talk about that later. There are two types of joints we'll be looking at, as we've seen. One is a free joint. Okay, so that would be if you have an object like the hello.xml and it's moving in space, it'll have its own dynamics. So x, y, z, theta, x dot y dot z dot theta dot p dot theta dot psi dot. And the other one is a chain. For that, we'll have a revolute or a prismatic joint. We've not seen too many prismatic joints, but actually we've not seen any example of prismatic joint, but that will be a chain. So it will be a manipulator like this. Okay, so when it's constrained, when it's free, you have 6 degrees of freedom, period. That's it. But for a revolute joint, you only have 1 degree of freedom each joint, right? So 1 DOF, DOF. So when there's a chain, it's constrained, and we need a different way of describing the motion. So let's look at both these joints. The free joint first. So the caricature I have for the free joint is the one we've drawn so many times. We have a x, y, z, or that's like the base frame. There's an object at this frame. This is like the initial position. And then the frame or the object moves. As it moves, we attach the frame to the object, and that frame also moves. So let's say that the frame is like this. So that x1, y1, z1. Okay, and then we had written down how to describe the frame. We have the origin of the frame, which is here, and then the rotation for this is R10 space. This O10 is basically the position of this. So we wrote down H10 as R10, 0, O10, 1. Okay, now if you want to compute the linear velocity, how fast does that object move in frame x1, y1 with respect to 0, you just have to take the derivative of O10. So this will be, this will give you x dot, y dot, z dot. It's very simple. However, the angular velocity, which is what we're going to spend a lot of time, is given by the rate of change of R1 dot. Okay, so the question is, how is this related to the angular velocity, right? Because the way we describe a body is through its angular velocity. But the notion is that if you take the derivative of h, you should get angular velocity. So we need to somehow relate r dot with the angular velocity. Okay, so we'll get to that next. D4, okay. So just what we're going to do is, before we get to the angular velocity, let's just talk a little bit about 2D versus 3D. Because it's easy to understand angular velocity in 2D, and we can take that in 3D. hopefully. So in 2D, if we have say a line segment like this, it rotates, or a body or the axis of that, it rotates by an angle theta, then this rotation is clearly about the z-axis, right? Theta dot. So this is I or x, y, z. So in 2D, we can write omega, which is the angular velocity, and I'm going to write a vector z simply theta dot k. K being the unit vector along z. Okay. Now in 3D, if you have rotations, omega x, omega y, omega z, turns out that the net omega is not equal to omega x I plus omega y j plus omega z k. This does not hold true. This is very much like how rotations, you just take rotations, they're not commutative. Same way, angular velocity, you just cannot add them in three dimensions. So that's a major difference. And that's where we'll get to. We'll try to find a formula for that. Now, the other thing which we want to remember is that in 2D, we can compute the velocity as, or the linear velocity as omega cross k. What is this? Well, if you have an object, and if you can, if you want to compute, this is the origin, and this is r, then the velocity of this point is basically v, and the formula for that is given as, say this is omega, and this is the correct vector omega. If you know omega, and if you know the distance from the origin, this origin is at not moving. Now this thing is true in 2D and 3D. It just holds in both dimensions. Okay, this holds true. And we'll use this expression that V equals omega cross R holds true in 2D and 3D. However, the angular velocity, you just cannot take angular velocity of different axes and just add them up. That will not hold true. Okay, so now we'll get to the main crux of it. We want to figure out how this R dot is related to omega. Okay, so that's our next goal. Our goal is to relate R dot to omega. Okay, so so this is going to be a little bit boring. It's basically a derivation, but I think it's kind of important because you will see this formula, the final formula, which relates then, but you will not know how it comes, but it comes by some matrix manipulation. So this is true for a rotation matrix. They are orthogonal. That is, if you take R and you multiply the transpose, you should get I. It should true for all rotation matrices. So we can take the derivative with respect to time. So we have R dot R transpose equals, sorry, plus R times R dot transpose equals 0. So what I've done is chain rule. I need to take the derivative of each of those terms by treating the other one as a constant. That's what I did. And then I is the identity, it's constant. Now what I can do here is I can use a property of the transpose. So use the property. I don't know if you've seen this before, but if you have AB transpose, so or AB transpose of AB, then that's the same as B transpose A transpose. And then A is the same as A transpose of transpose. So you can take the transpose twice and you'll get A. That's kind of obvious. But the second one, the first one is less obvious, but that's true. So let's use this R transpose. Okay, I'm going to take the second expression and then write those two transposes. So one transpose, second transpose, very similar to this is the same as this is what I did. Now R dot, oh, this is equal to 0. Now what I'm going to do is, given that this is AB transpose, I'm going to use the first identity. So I can write this as B transpose A transpose, which is R transpose of transpose is R dot R transpose. So this is what I did here is use this fact on just this expressions to get this. So this stayed as it is, and the other thing, I just took the, okay, so this is equal to 0. Okay, now there's something which I don't know if you know about this, but if you call this as a matrix S, you have the same matrix S here, S plus S transpose is 0. It's the same matrix. There's a special matrix which has this property. It's called a skew symmetric matrix. Okay, anything which follows this property is called a skew symmetric matrix. A skew symmetric matrix will have all diagonal terms as 0. Example would be if you want to compute S of A, where A is AX, AY, AZ, then that would be, if I'm remembering correctly, omega A, Z, AY, A0, AX. You just confirm this. Yeah. Where A is AX, AY, AZ. So if you have AX, AY, AZ, then you can write it like this. It's one of your homework problems. If you remember first homework, you were use this to do cross product. Okay, so this is saying that let's just call this some S of A. I don't know what that A is, but we need to find that. So this is A, where I need to find what A is. So what we can do is from these expressions, we can see that R dot R transpose is S of A. So what is A? And A, I wrote it down as AX, AX, AY, AZ. Okay, so we have to find that. So here's what we'll do. We can write the position of a body which is floating in the air. Let's assume that it's only rotating, it's not translating, as R times RB, where R is position in world frame and RB is position in the body frame. Okay, so that vector RB is fixed. It's not going to change. But if you want to describe its motion in the world frame, then you just multiply with the rotation matrix. That's like a property of the rotation matrix. Okay, so what we'll do is we'll differentiate this expression with respect to time with respect to time. So we have R dot equals R dot times RB plus R times RB dot, chain rule. But R dot B is 0 because remember that's a vector in the body frame, and that vector in the body frame is attached to the body. As the body moves, that vector is fixed. It's not going to change with respect to the body. So that's 0. So we're left with R dot equals R dot times RB. So now what we'll do is we'll actually substitute. Let's call this from 1. 1 is this expression we wrote down last time, is R dot equals S of A times R times RB. But what is R times RB? It's right here. S of A times S of A times R. So this is from 2. Okay, so we have R dot is S of A times R. Let me take that and show you something. So we have an expression for R dot. So we have R dot is, I'm just rewriting that, S of A times R, but we know that A cross B is same as S of A times B, right? This is a example well, this was one of the problems you did for your homework 1, I believe, where you can write the cross product of a vector A cross B as the skew symmetric matrix times B. So everything on the left is a vector operation, cross product, but everything on the right is a matrix operation. This is a 3 cross 3 multiplied with 3 cross 1 to give you a 3 cross 1, which is also the result of this. Okay, so with that, what we can do is we can write this as R dot equals A cross R. Okay, but we know that V equals R dot is omega cross R, right? This is a property of the linear velocity. It is always omega cross R. So it has to be that A is the same as omega. Well, you can write it like this. So this is same as omega. Okay, in other words, what we've shown that R dot, which is S of A times R, is the same as S of omega times R, where S of omega is a skew symmetric matrix, 0 minus omega x, omega y, omega x, 0 minus omega z, 0, and then, sorry, omega z Okay, so omega is the angular velocity of the object in the world frame, and that is related to r dot.